This module of the online training for the ODOT Analysis and Traffic Simulation, or OATS, manual provides information on the scoping of the traffic analysis. In this module, you'll be introduced to the scoping elements required for performing traffic analysis for ODOT. To aid in developing the scope, a traffic analysis scoping checklist has been developed. This module will also detail the components of the checklist. The traffic analysis scope is the foundation for a solid traffic analysis. A properly prepared traffic analysis scope documents the assumptions and methodologies to be used for the analysis. It can also be used to help prepare the man-hour estimates for performing the work. The traffic analysis scope should be tailored to the complexity of the project. A simple rural intersection would be scoped much differently than an urban interstate with a system interchange. The scope should also be used to raise concerns and to resolve them early in the process. Some of these resolutions may lead to changes in the analysis, which can be accounted for in the scoping process prior to the fee development, which can prevent a fee modification later in the analysis. The traffic analysis scoping document is prepared by the ODOT District Project Manager prior to the development of the consultant's fee proposal. It should be reviewed and approved by the Office of Roadway Engineering, also known as ORE, for projects that will involve ORE. These projects include interchange studies, which include interchange justification studies, interchange modification studies, or interchange operations studies, feasibility studies involving interchanges, and alternatives evaluation reports, or AERs, involving interchanges. Most importantly, the traffic analysis scoping document must be completed in advance of the early coordination meeting with modeling and forecasting, as it could affect their work on the project. The scoping document is a 6-page PDF form available on the ODOT website. Each of the scoping elements is included in the form and will be discussed in more detail in this module. Throughout this module, a sample traffic analysis scoping document will be completed as each element is discussed. For this exercise, the sample project is State Route 315 from Bethel Road to North Broadway in Columbus. There are a number of elements that should be included in the scope and scoping document. Each of these items will be discussed in more detail in this module. Furthermore, many of these elements have dedicated chapters in the OATS manual that include specific details that can be used for reference when performing the analysis. There are two types of traffic analysis: standard and complex. The majority of projects will be standard type. These types of analysis use the default values from the software packages like saturation flow rates or other easily obtained data and have minimal calibration and validation needs. Nearly all highway capacity software, or HCS, analysis and most small transmodeler analysis will be the standard type. Complex type projects will require the analysis of existing conditions so that the model can be calibrated to match real-life conditions. As a result, the data collection can be labor-intensive, especially since the model does not use as many default or standard values as a standard analysis type. Large freeway corridors with multiple interchanges and other high-risk projects are examples of complex analysis types. Here's a snippet from the traffic analysis scoping document for our sample project. The project name, PID, district, county, and route are all listed. As with most projects, this analysis is a standard type and will not require extensive calibration and validation. The project description details the location, context, and background information for the project being analyzed. A vicinity map and project location map must also be included with the traffic analysis scoping document. The vicinity map shows the larger region in which the project is located. The project location map is more focused in on the study area. Here's the project description and map for the sample project of State Route 315 from Bethel Road to North Broadway. The project description simply reads, "The project is located within the city of Columbus. Daily congestion occurs along State Route 315 southbound during the AM peak hour and State Route 315 northbound during the PM peak hour. In addition, the closely spaced intersections of Olentangy River Road and the northbound State Route 315 ramp terminal along Henderson Road experience congestion and long queues." The traffic analysis objectives should clearly identify the performance problem or goal in which the analysis seeks to answer and the intended use and decision makers of the traffic analysis results. This objective will help shape how the project is scoped. For this sample project, the goal of the study is to identify short and medium-term solutions to reduce delay and congestion along Henderson Road. In addition, a long-term solution to improve overall operations along State Route 315 and Henderson Road will be developed. A possible long-term solution could include a northbound auxiliary lane on State Route 315 between North Broadway and Henderson Road. The analysis boundary limits should include all locations that could be affected by a proposed improvement. While several intersections could be impacted by an improvement, boundaries should be logically drawn at the locations with the most impact to the traffic flows and/or are the closest proximity to the study location. For example, if two ramp terminal intersections are being improved, it would be sensible to include the two adjacent signalized intersections on the arterial. The analysis limits for several types of studies are already defined in other ODOT manuals and guidelines. The analysis limits for traffic impact studies are contained in the State Highway Access Management Manual. For interchange justification studies, interchange modification studies, and interchange operations studies, the analysis limits can be found in the ODOT Traffic Academy course material for interchange studies. Corridor studies not involving an interchange will typically include the study intersections along the corridor plus the first adjacent signalized intersection on either side of the study intersections. Model limits should be extended so that all entry links operate in undersaturated conditions, meaning that the segments on the boundary of the study area are not operating over capacity. If it is impractical that the study limits be expanded so the network is free of queuing that extends beyond the study limits, Transmodeler should be used for the analysis. Chapter 2 of the OATS manual includes more details about selecting appropriate boundary limits. A scaled map showing all study interchanges and intersections must be included with the traffic analysis scoping document. Also, the geometric limits should be described as shown here for the sample project. For most analysis, the weekday AM and PM periods will be all that is necessary. Specific locations may require weekend, school arrival, and/or release periods, or off-peak period analysis. Check the surrounding land uses to determine if periods other than just the traditional morning and afternoon peak period should be analyzed. Intersections around shopping malls or churches may need to be analyzed during the weekend, while intersections near factories with second and third shifts may need to be analyzed during off-peak hours. In the scoping document, justification should be provided for why peaks other than the weekday AM and PM periods are being analyzed. Only the design year, which is typically 20 years after the opening year, will be analyzed for most projects. Depending on the project type, the analysis could include existing conditions and/or additional interim design years. These additional years should be clearly identified in the scoping document. Instances when an interim year may be included are traffic impact studies where design year could be 10 years after the opening year, or an additional interim year may be evaluated based on improvements in level of development. Corridor and feasibility studies where the existing conditions are useful for determining the purpose and need of the project and gaining stakeholder public buy-in for the analysis. Ramp clear projects that are trying to address existing congestion with simple, low-cost countermeasures and are not addressing long-term issues. Safety studies that typically just focus on the existing traffic volumes. Sensitivity analysis where the analyst is trying to determine what year different improvements will be needed. Phase solutions where only part of the improvement is being constructed initially. For this situation, it may be desirable to know how the initial improvement will operate in an interim year, for example, 10 years after construction. Locations where the design year will operate at level of service F and you want to compare how alternatives will work for an interim year. Complex type projects which will require the calibration and validation of existing conditions. See Chapter 2 for more details regarding study periods and analysis years. For the sample project, only the AM and PM periods are being analyzed for a design year of 2040. For ODOT projects, two analysis tools are available: Highway Capacity Software, also known as HCS, and Transmodeler. HCS is a deterministic or equation-based tool that implements the methodologies in the Highway Capacity Manual, or the HCM. It is an ODOT requirement to use HCS for all analysis when possible. Transmodeler is a micro-simulation tool that can model most roadway and intersections. As a stochastic tool, Transmodeler employs randomness in the computational methods to model real-world traffic conditions. While HCS is the preferred software for ODOT analysis because it is simpler to use, Transmodeler may be required to evaluate heavily congested conditions, complex geometric conditions such as a complex weave, and system-level impacts beyond the capabilities of HCS. With approval from ODOT, additional analysis tools may be used on a project-by-project basis. These include the Synchro Sim Traffic software package and Sidra. ODOT guidance on the use of these software products can be found in Section 401 and Figures 401-14 of the Location and Design Manual, L&D, Volume 1. While the OATS manual is written specifically for the use of HCS and Transmodeler, many of the HCS elements in this manual are applicable to Synchro and Sidra analysis, such as peak hour factor guidance. Likewise, many of the Transmodeler elements in the OATS manual are applicable to sim traffic analysis. The analyst should apply these elements whenever possible. Chapter 3 details the specifics on selecting the appropriate analysis tool. The tool selection and reasoning should be justified and stated clearly in the scoping document. In the case of the sample project, both HCS and Transmodeler will be used. Details regarding why Transmodeler is required are provided in the description on the Traffic Analysis Scoping Document form. Data is crucial for accurate analysis. In addition to using it for critical analysis inputs, data is used for calibration and validation on complex type projects. Chapter 4 details the data needs as well as the collection methods to be used when obtaining the data. Some data can be obtained from existing sources, while other information will require field measurements. On the scoping form, the data collection needs and locations shall be explicitly stated. In the case of the sample project, 12-hour turning movement counts will be collected at all study intersections and a 48-hour segment count on State Route 315. Both types of counts will be collected using MyoVision video technologies. Counts will be collected on a Tuesday, Wednesday, or Thursday when schools are in session. Average speeds and travel times are not needed for this project. Q-links will also be collected using visual observations. These observations will be conducted on the same day as the traffic counts. Existing signal timings will be provided by the City of Columbus. Because there is not a lot of pedestrian traffic in the study area and pedestrian push buttons and signal heads are provided at the study intersections, pedestrian timings do not need to be accommodated within the phase times. Free flow speeds are not required for this project. However, lane utilization information is needed since lane usage is not evenly distributed at Henderson Road and Olentangy River Road. The process in which the lane utilization will be measured is detailed in the scoping document. The analysis scoping document should include the demand forecasting procedure for future year analysis. Future years include opening, design, and interim years as defined by the analysis period. Traffic forecasts used in HCS are typically turning movements. However, Transmodeler can use turning movements for origin and destination (OD) tables. OD tables may be especially beneficial when new connections are constructed or when route choices may be altered because of the improvement being analyzed. For ODOT projects, there are 4 primary ways to develop traffic forecasts. Using the Simplified Highway Forecasting Tool, or SHIFT, growth rates for state roadways are generated using historic trend line analysis and travel demand model of record. SHIFT growth rates can be obtained from District Certified Traffic Coordinator. With certified traffic forecasts are developed in accordance with the methodologies outlined in ODOT's Ohio Traffic Forecasting Manual. The Office of Statewide Planning, Modeling, and Forecasting will either complete or review and approve these forecasts. Planning level forecasts should be developed per ODOT's Ohio Traffic Forecasting Manual, Volume 3. Another method uses the Simulation Demand Estimator, or SDE tool. When using the SDE tool, analysts should coordinate with ODOT modeling and forecasting as early as possible in the project. The SDE tool will typically only be used for very large corridor studies where the diversion of traffic to alternate routes are anticipated. For the sample project, the consultant will develop traffic forecasts using shift growth rates. The project alternatives should be detailed in the scoping process if known. It is the requirement of ODOT to perform design year no-build conditions analysis of the roadway network for all projects. The no-build analysis is used as a baseline to compare build alternatives. The no-build conditions should include not only existing projects under development, but also committed improvements with program funding expected to be completed by the design year. For complex type projects, the existing conditions analysis is required and will be used for calibration and validation of the analysis. While the specific configurations being analyzed as build conditions may not be known at the time of scoping, the number of alternatives being analyzed should be identified in the scoping document. In the sample project, an existing conditions analysis is not required. The no-build condition along with 4 build alternatives will be analyzed. Note that while the analysts may have ideas for what the build alternatives might include, the details are not provided in the scoping document. Numerical outputs from the traffic analysis are the measures of effectiveness, MOEs, which are metrics used to assess the performance of an isolated location or system. MOEs are also used to compare the performance under various design or improvement alternatives. Level of service is a readily recognizable indicator of traffic operations and has been widely used by different agencies when evaluating the traffic operations performance of facilities. However, level of service alone does not necessarily give insight about the overall performance of the facility. Thus, additional quantifiable measures should be included in the analysis to better assess the performance of the location or network being analyzed. At a minimum, the outputs of level of service, delay or density, 95th percentile queue lengths, volume to capacity ratios, and queue storage ratios should be reported for all analysis. Additional MOEs can be reported based on the project being analyzed. Analysts should work with the ODOT project manager during the scoping process to determine if additional MOEs are required. Such MOEs could include average speed for the corridor or study area, travel times, vehicle hours delay, and density for the facility. Additional guidance on the MOEs are provided in Chapter 8. All of the required performance measures will be reported for this project. Additionally, travel times for the State Route 315 mainline corridor will be obtained from both HCS and Transmodeler as another metric to use to compare their alternatives. Documentation requirements for a traffic analysis should be established as part of the traffic analysis scoping. The scope of the traffic analysis should describe how the results will be presented to the intended audience, such as policymakers and the public. Documentation is also necessary to enable a reviewer to independently confirm analysis assumptions, analysis methodology, input data, outputs, and if necessary, reproduce the same results presented by the analyst. The documentation necessary to support traffic analysis should be proportional to the size of the project and complexity of the analysis. Specific documentation requirements for traffic operational analysis are provided in Chapter 9. In summary, the traffic analysis scoping document is a helpful tool that is used to document assumptions and methodologies that will be employed during the traffic analysis. The document also is used to help determine the level of effort required to perform the analysis when preparing man-hour estimates. The form is usually completed by the ODOT District Project Manager and is only subject to review by ORE if ORE will be reviewing the analysis. It must be completed in advance of the early coordination meeting with modeling and forecasting. All of the elements included in the scoping document are described in more detail in specific chapters throughout the OATS manual.